A generic drug used to treat a particular condition has a success rate of 51%. A company is developing two new drugs, A and B, to treat the condition. They carried out clinical trials on two groups of 500 patients suffering from the condition. The results show that drug A was successful in the case of 296 patients. The company claims that drug A is more successful in treating the condition than the generic drug. So we will use a hypothesis test at the 5% level of significance to decide whether there is sufficient evidence to justify the company's claim. So I'm going to let P stand for the success rate for drug A. Now P is the population proportion of those who were successfully treated by drug A. The null hypothesis is that drug A is no different than our generic drug, which has a success rate of 51%. So the null hypothesis is that P is just 0.51. Now our alternative hypothesis is that drug A is more successful. So in this case, our alternative hypothesis is that P is greater than 0.51. Now, as we've seen previously, if we consider all our sample proportions, that's proportions of successfully treated people from samples of size n, all of them follow an approximately normal distribution with mean equal to the population proportion P. So under the null hypothesis, P is 0.51. Approximately 95% of all our sample proportions, if we were to take many samples, would lie between these two values. Okay, between P minus 1 over root n and P plus 1 over root n. So I'm using the simpler formula for the margin of error okay, that we saw in the previous video. We have a more complicated formula that can be simplified to 1 over root n. So anyway, I've calculated P minus 1 over root n. Okay, n is 500, 1 over root 500 is 0.045. 0.51 minus 0.045 is 0.465. 0.51 plus 0.045 is 0.55. Okay, from our sample, 296 out of 500 were successfully treated by drug A. So our sample proportion, our estimate for the population proportion, is 0.592. As we saw before, to see whether or not our sample proportion is in the rejection region, we can get the distance of P hat to P. That's this distance here. So we don't necessarily have to calculate these two numbers. So if we calculate that distance, okay, subtract these numbers. If it's negative, you just take the magnitude, get the distance, positive value. Compared to the margin of error, which is this distance here, that's just 1 over root n. Okay, we can see that the distance between P and P hat is greater than 1 over root n. So that tells us that our value of P hat is in this rejection region. Now, as a matter of fact, we want our P hat to be somewhere at the right tail, because remember, to reject a null hypothesis, we're hoping to get a value of P that's greater than 0.51. So really we're ignoring the left tail of this distribution. So we should really be doing a one-tail test here and make our rejection region, 5% rejection region, all in the right tail of our distribution. So this is the same distribution as before, but 5% is in this right tail rather than being split into two tails of area 2.5% each. It's clear that if our P hat is in this region over here, well, it's certainly going to be in the rejection region here, because this tail has greater area than this tail up here. So you can see anyway that we will reject the null hypothesis. We conclude that drug A is better than the generic drug. Now the key word here is better, not that drug A works differently from drug B. The alternative hypothesis here is that P could have been just not equal to 0.51. So the success rate for drug A could have been worse than or better than the success rate for the generic drug. If that was the case, we would just have this two-tail test, but in reality we need a one-tail test. Okay, normally when we test a drug's efficacy, we want to see if it's better than some generic drug, not so much that it's different from it. We certainly don't want it to be worse than some other drug. The null hypothesis was accepted for drug B. Let's look at p hat for drug B. So to calculate the sample proportion of those successfully treated by drug B, we get the number of people successfully treated and divide by the sample size. Well, in the group for drug B we had just as many people as the group for drug A, so it's 500 people. Estimate the greatest number of patients in that trial who could have been successfully treated with drug B. First of all, I just want to show an incorrect method for answering this question. Okay, the incorrect method is to use the fact that if the null hypothesis is true, if p is 0.51 for drug B, well, 95% or approximately 95% of all sample proportions p hat would lie between this value here and this value here. And the maximum value that our sample proportion could have is 0.555. So that maximum proportion gives us a maximum number for those successfully treated. Okay, so I'm just letting k be the number of people successfully treated. We would solve this equation. We get a value for k. Of course, k must be an integer. It's the number of people. We don't round up to 278 because then we're into the rejection region. So we have to round down to 277. So anyway, that's an incorrect method. The reason why is because we're assuming here that the alternative hypothesis is that p is not equal to 0.51, so we have this two-tailed test. In reality, we should use this one-tailed test. So that means we need to figure out what this value here is. As I explained in the previous video, our distribution of the p hats, all the sample proportions, is approximately normal, with mean equal to the population proportion, 0.51. We're assuming the null hypothesis is true, so the population proportion is indeed 0.51. And the standard deviation is given by this quantity here. Remember, the more accurate margin of error for this, for the 95% population proportion, is given by this formula here. So the standard deviation is just half of that. Okay, the margin of error is actually 2 sigma. So we need to calculate this thing if we want to find out what this point here is on the distribution. So we need to plug in for n and p. So all our sample proportions come from samples of size 500. So calculating this thing here, we find that sigma is 0.022. Now, to find this point, which I'm calling x, we need to transform to our standard normal distribution. So we want the value of z such that the area to the left is 0.95. And if you look this up in your tables, you'll see that that value happens when z is 1.64. Well, approximately 1.64. So here's our formula for converting x to z. So we just need to rearrange this to get x. So multiply both sides by sigma and add mu to both sides. So sigma is 0.022. Our z value is 1.64. And mu, the mean of this distribution, is 0.51. We get 0.5461. We can now correctly answer this question. So the null hypothesis has been accepted for drug B. So that means our p hat must lie somewhere along this line here. So I'll call the number successfully treated k. So we divide that by 500 to calculate our sample proportion. And the maximum value it can have is 0.5461. And that will lead to a maximum value for k. So rounding down, we get that the maximum possible number of people that were successfully treated by drug B is 273.